Hi guys, so where we left off last time was this idea that if you've got two objects, a warmer object and a cooler object, heat is the transfer of thermal energy from one object to the other, and the temperature of each object is a measure of how much thermal energy is stored in those objects. So what we're going to look at today is how to do some calculations with this. So first of all, we need to look at how we actually measure temperature. So we normally measure temperature in degrees Celsius, but it turns out scientists have another scale that they use often. So it's based on this idea of absolute zero, which is the temperature when the particles in the substance will actually stop moving and have no more kinetic energy. So this actually is approximately negative 273 degrees Celsius, and this temperature scale that they use is called the Kelvin scale, and it actually says that negative 273 degrees Celsius is 0 degrees Kelvin, and then it starts going up from there. Now the nice thing about this is that 1 degree Kelvin is the same as 1 degree Celsius. They just have different starting points. So as you can see in this table, at 0 Kelvin, that's negative 273. At positive 273 Kelvin, that's where we've gotten up to 0 Celsius. 300 degrees Kelvin is about 27 degrees Celsius. So you'll often see room temperature listed as 295 Kelvin, because that's about 22 degrees Celsius. And then 100 degrees Celsius is 373 degrees Kelvin, so that's the boiling point of water. And if you forget how to sort of convert this, it's fairly simple. The temperature in Kelvin is just the temperature in degrees Celsius, add on 273. And then the reverse. So if you want the degrees Celsius, you can take the Kelvin and minus 273. Okay, so when an object will actually absorb heat, which is energy, its thermal energy is going to increase, and so we know that its temperature will increase as well. So for example, if we imagine there's 100 joules of thermal energy being transferred into two different objects, object 1 and object 2, will they both increase their temperature by the same amount? Well, they're different, aren't they? So it would seem kind of logical that maybe they wouldn't. The next question is, what will actually affect this change in temperature? And it turns out there is a pretty simple formula that relates temperature and heat. So it's Q equals mc delta T. So the symbol Q actually represents the heat, or the thermal energy transferred to or from the object, and that's measured in joules, just like all types of energy. M is the mass of the object, and that's measured in grams, which is a little bit different to some other stuff that we've done, which is often kilograms. C, this letter C, is what's called the specific heat capacity of the object, and I'll talk a bit more about that in a moment, but it's basically related to whatever it's made out of. And then delta T, delta means change in. This is the change in temperature, and that can be in Kelvin or degrees Celsius. It doesn't really matter because they both go up and down by the same amount. And we're talking only about the change in temperature, not the actual temperature of the object. If we rearrange this formula mathematically, there's two ones that you sort of crop up quite a bit. So delta T is equal to Q over MC. And if we rearrange it slightly differently, we can have C equals Q over M delta T. Well, why would we use these? The first one here, we might use this if we wanted to figure out how much the temperature has changed based on the heat and the mass and the material. The second one is if we wanted to work out what the specific heat capacity of the object was, if we knew what the heat was, the mass was, and the delta T value. So what is this value C, the specific heat capacity? Well, like I said, it depends on the material that is losing or gaining heat. And it's defined as the heat energy required to raise the temperature of 1 gram of this material by 1 degree Kelvin or Celsius, because they go up and down by the same amount. So for example, here's some different materials, and whether they're a gas or a solid will actually affect the specific heat capacity, and these are the specific heat capacity values. So probably one of the most important ones is water. So if you have a look here, water is 4.18, but we often round that off to 4.2. But you can see if water does become steam, it actually has a slightly lower specific heat capacity. So that means less energy is required to get that change in temperature. So if we go on to a couple of examples here. So let's say we want to calculate the heat required to raise 400 grams of water from a starting temperature of 20 degrees Celsius to a finishing temperature of 65 degrees Celsius. So we're trying to figure out what Q is, this heat that's going into the system, and we're going to follow the same process we normally would and write down what we know. So we know that the mass is 400 grams. We know that the specific heat capacity is 4.2, so that's from the table on the previous page. And often in a question like this that would be given, but you can always look them up. The delta T value is just the change in temperature, so that's the finishing temperature minus the starting, so 45 degrees Kelvin or Celsius, it doesn't matter for delta T. So it's gone up by 45 to get from here to here. And then we're going to write down the formula that we're going to use, which is for Q, so that's what we're trying to figure out, so Q equals MC delta T. And if we substitute in our values, so M is 400, C is 4.2, and delta T is 45, and then work that out. It's about 75,600 joules, so quite a lot of energy. And we can round that off. If we bring that back, that decimal place back by 3 points, we can change that into kilojoules, so 75.6 kilojoules. So that's how you would work out the heat if you knew the mass, the specific heat capacity, and the change in temperature. We'll just do a second example. So here now we've got a 1 kilogram steel panel. So this is the sort of question that people might look at when they're designing like an air conditioning system or something along those lines. And that's absorbing 10,000 joules of heat. So if the starting temperature of this panel was 25 degrees Celsius, we want to find its final temperature. Well, let's start again by writing down what we already know. So we know that the mass is a kilogram, which is 1,000 grams. Remember, for these questions, you do need to put everything in grams, not kilograms. The heat absorbed is 10,000 joules. So we'll write that down. The specific heat capacity for steel, so we've been told the material, I just looked that up on the table, is 0.466 joules per kilogram per Kelvin. And then I'm going to write down my formula. So this is one of those rearranged versions. So delta T equals Q over MC. And then I'm going to put in those numbers. So Q is 10,000, M is 1,000, and C is 0.466. And if I work that out, I get a delta T of 21.46 degrees C. Or Kelvin, doesn't matter, again. Does that tell me the answer? Well, no, because I know that it started at 25 and we want to find the final temperature. So what that means is I'm going to get my 25 and I'm going to add the 21.46 to give me my final temperature here of 46.46 degrees Celsius. Okay, I hope that makes sense, and thank you for watching.